Hey there, everybody. Welcome to Physics 200 for Monday, the 13th of April. Let's start off with a couple jokes. How many Germans does it take to screw in a light bulb? The answer is just one. They're very efficient and they're not very funny. Um, how about another one? How many Harvard students does it take to screw in a light bulb? The answer again is just one. They hold the light bulb and the universe revolves around them. As always, if you have some good jokes, send them to me and keep those memes coming. They are hilarious. Today, we're going to move from talking about atomic models. We got to the point where we saw that the nuclear model of Rutherford was good and that Bohr capitalized on it and could at least get the spectrum, emission spectrum and absorption spectrum for hydrogen, but that there were a lot of problems with the Bohr model and that left us having to use the wave function psi. And so today we're going to actually take a step that isn't usually discussed very often in books, but we're going to talk about getting to the problem we need to solve for the Schrodinger wave equation. On our schedule here, we're on Monday the 13th. We're talking about the two-body problem for the Schrodinger wave equation. On Wednesday, we'll talk about separation of variables. We'll talk about outlining that on Thursday regarding your paper. And then on Friday, we'll get to the angular wave function for the Schrodinger wave equation. And notice then, we basically have this week and next week, and then we're pretty much done. So for your reading, sort of a weird one. I'd like you to read page 148 of your book, just that, and then section 7.1 of the book, and think about the following three things. What is the reduced mass mu? Why do we need to worry about the reduced mass? And what is the Laplacian and spherical coordinates? So now here's where I ask you to take a pause. Go do your reading and come on back. Okay, welcome back. So the Schrodinger wave equation for the hydrogen atom is really our goal here, right? We want to understand the hydrogen atom. Our tool is going to be the Schrodinger wave equation right here, written in its nicest form, minus h bar squared over 2m times the Laplacian del squared of psi plus v psi equals e psi. Oftentimes when I write this capital psi, I'll mean that to mean some sort of total wave function, which we'll see here in a minute. This v here could be any potential. This e here is the eigenvalue energy. So our real hydrogen problem has two bodies. We have the proton here in the center. We have the electron going around. And really, we need to apply this Schrodinger wave equation for both bodies simultaneously, which means we have to worry about, the x, y, and z coordinates of the proton, the x, y, and z coordinates of the electron. We have to worry about a six-dimensional differential equation we need to solve. That's awful. Now, our solution, though, is to divide the problem into two parts, to consider the center, just like we do in classical mechanics. If we have some object here that's rotating and it's translating, what we do is we divide the problem into two parts. We talk about the translation of the center of mass and then the rotation about the center of mass. And so that's our goal here as well, is we want to break up our problem into the center of mass motion, part one here, and then part two, the relative motion. So to do that, we define two new coordinates, vector r, that's what the bold means, vector r, which is vector r1 minus vector r2, where these distances are measured, the relative position between two objects, and then capital R, the center of mass position, which is the center of mass of the system. Let's see how we use those. If we do that, then the Schrodinger wave equation for the total wave function here, and there should be a psi tot on the right-hand side, breaks up into two parts. One part for the center of mass motion, and a second part for the relative motion. You'll know where the wave function then is the product of the center of mass motion, center of mass wave function, and the relative wave function. If you take this wave function here and you plug it in here, you'll see that you can break it up into two parts. One thing that's not clear, if you choose to do that, is that this del squared is in center of mass or capital coordinates, And this del squared is in little or relative coordinates. So you can literally break this problem into these two separate problems. I'm not going to go through that math because you already know when something is spinning through the air, you can break it up into its center of mass motion and then its motion around the center of mass. Okay. Another thing you'll notice here is that there's no potential for the center of mass motion. That's because our atom doesn't feel any potential. It's just sitting there in regular space. Whereas our relative motion problem, there is a potential between the electron and the proton. Now for the center of mass solution, that's really easy. We've seen this problem before. The second derivative of the wave function is equal to the negative times the wave function itself. That gives us a solution that is some constant that I've left off, e to the plus or minus I k, where k is the center of mass wave number times r. This is just a plane wave solution. All it says is that our object, as it's translating along, as the center of mass is translating along, acts like a plane wave. The more interesting part is the relative motion part. Now we have to be careful here because in this relative motion part, the coordinates are relative coordinates between the electron and the proton. But that's not really terribly surprising because it's weird if I try and say, I have a proton that's my head, I have an electron sitting here, and we're to find a coordinate system that's my chest, and we're going to measure those positions relative to the origin of that coordinate system. What we always do is take the relative coordinates between the electron and the proton and worry about that. So that's really not a big surprise. The thing that is a surprise is this mass m and the h bar squared over 2m. Notice that's a mu now. This is what's called the reduced mass, and it's given by m1 m2 over m1 plus m2. That's just stated in your book. Let's actually see where that comes from. Okay, so getting the reduced mass. Here's our problem. Here's the center of mass at x. Here's my proton, which is traveling around the center of mass like this. Here's my electron, which is traveling around the center of mass like that. The electron is at a distance r2 from the center of mass. The proton is at a distance of r1 from the center of mass. So the total distance between them is r1 plus r2, but the vector difference in vector between these is the vector r1 minus the vector r2. Capital R is the location of the center of mass relative to some point. So if I want to solve for r1, that's just going to be the center of mass position plus m2 over m1 plus m2 times r. If you're not certain, check it out. You'll see that it's right. R2 is the center of mass position minus m1 over m1 plus m2 times r. Now, if we take f equals ma for each object, and we take object number 1's f equals ma and multiply by mass 2, we get this expression. Notice here, this is ma for object 1, m1 times its second derivative right here is equal to f. We then multiply both sides by m2. We do the same thing for object 2 and multiply by m1. Here's m2a2 is equal to f. Notice there's a negative sign in front because the force on object 1 due to object 2 this way is the opposite of the force of object 2 on object 1 this way. Those vector forces are in opposite directions, so we need a negative sign right here. Again, we multiply both sides by m1. What that allows us to do is to subtract these two. So we get m2, m1, that's common on both left-hand sides, times the second derivative of r1 minus the second derivative of r2, is equal to m2 minus a negative m1, or m2 plus m1, times our force F. Okay, notice that r1 minus r2 is simply the relative to position r. And so we get m2, m1 is the second derivative of the relative position r is equal to m1 plus m2 times F. Or mu times the second derivative of the relative position r is equal to F. So mathematically, what we've done here is we've taken this set of two equations here, F equals ma for object 1 and F equals ma for object 2, and we combine them to make F equals a reduced mass times a relative position. In other words, we've reduced a problem with two things I need to worry about to a problem with only one coordinate I need to worry about. And that makes life a lot easier. And that's the mathematical answer. Let's say physically, with that mu, physically, where does that come from? Well, physically, what it is we've taken this situation where we have a mass M2 and a mass M1 that are separated a distance R2 and R1 from the center of mass. And really, this should be R1, and this should be R2. And we've made this problem equal to this problem, where both objects are still separated by R1 plus R2, but now the central object acts as if it's infinitely big and doesn't move at all. And this outer object has a reduced mass. We call it a reduced mass because the two-body problem over here, two objects moving together, has been reduced to a one-body problem where the central object doesn't move and we only have to worry about the motion of the outer body around the center of mass. And there is our factor of mu. So we don't need to solve the two-body problem. Remember, when we think back, what we had were two bodies that were moving, the electron and the proton. We got rid of the center of mass motion. We still had in here two objects that were moving, but we've reduced it to this one object moving problem. And that's fantastic. We only have one problem to solve. Hey, we just have h bar squared over 2 mu instead of 2m. Del squared psi plus v psi equals e psi. That's great. That's the nice version. But then we remember Dr. Tever in Physics 201. We remember that del squared, that we're going to be doing this probably in spherical coordinates because our potential is spherically symmetric, right? It only depends on the radial distance r between the proton and the electron. So we're going to want to do this in spherical coordinates. If you remember, del squared in spherical coordinates is that. Yay. Using 201 in our spherical coordinates, our version of this is minus h bar squared over 2 mu times this nasty operator on psi, plus here's our potential, negative q over 4 pi epsilon naught psi is equal to e psi. And this right here, by the way, should be 2 q's, not just one, because it's potential energy, not a potential. This right here is the problem we're going to need to solve starting next time. Don't worry, we'll get through it. It will not be the end of the world. It will be worth it in the end. I hope you have a great day, and I look forward to chatting with you on Wednesday. Take care.